Today's computing forum is from Chuck Thacker, and he needs no introduction. He'll be talking about the D0.
You have probably heard about the D0, and I will tell you today what it is and what we're doing to make it become reality. The D0 is a machine computing system, and it has a lot of peripherals, and it looks approximately like an Alto, except it has a lot more power. And it is being built primarily for the XBS, including STD, who is the primary customer, for use in the Janus program, which is a very grandiose word processing product, and the ERIC program, which is a electronic copier, that is a copier which will spool documents onto a disk and then print them via a ROS. ERIC is actually a copying product as opposed to a computer printing product of the sort that we have around here. The reason for doing it is because we can get a thing that is sort of the machine that we want, rather than suffering the fortunes of whatever components are available. And we believe that the machine will provide a nice nucleus for real system products, things that you can configure in many ways to form many different kinds of functions. And the principal characteristic of these functions is that the hardware really enables them, but they are realized by software. I mean, this is a very software-intensive kind of thing. And we can, again, provide hardware that has programming characteristics for the programmers, which are determined by their needs rather than by the availability of components or what the logic designers want to produce this week. That's fairly unusual. I'll tell you a little about the way things are being done, and then I will get into the technical part of the thing. The program in EOD is organized in two groups, one here and one in Los Angeles. I am responsible for the part here, and there are 4 people who work over in another building on the program: Don Charnley, Tom Chang, Brian Rosen, and myself. And the group, exactly so. And the group in Palo Alto is primarily providing the overall technical direction for the thing and the development of the CPU, the microcode, and the tools that we're using to build the thing. There's a fair amount of Alto-based tools, SIL, that sort of thing. The group in Los Angeles is mainly doing the program management and coordination with the functional organizations in EOD. The way EOD is organized is a big matrix. There are a lot of functional organizations: drafting, design automation, components, circuits, things like that. And when you do a product program, those things all have to be coordinated. And Howard Kikita and some of his people are working on that. Also, all of the I/O controllers that are going to be used in the actual product version are being done in El Segundo. So that takes care of that. And the pieces that are being done for the D0 are these. These are modules. There are some slides a little later that show some bits and pieces of the production and debugging environment over in the other building for the CPU. Basically, the modules are 11 by 14 cards. They hold about 170 ICs. This machine is sometimes referred to as the MSI D0, and in good pipeline fashion, there is a machine beginning to be designed now, which is the follow-on product to this machine. This machine will be introduced in late '79, early 1980, and the follow-on machine will be a couple of years later, a year to a couple of years later. The modules that we're building right now are 4 types of CPU boards. The CPU is 4 modules. A storage module, which is 96,000 words by 16 bits on one board, very dense board. A controller for a full-page display of somewhat higher resolution than the Alto. It is, in fact, the display that is being used on the 850 word processor. A controller for a disk, a 7 megabyte, 7 to 28 megabyte Shugart disk, a very nice new disk that they have just come out with. Controller for the Xerox wire. The Xerox wire, as most of you probably know, is the sort of logical successor to the Ethernet. A bit faster and a bit more reliable and a bit more robust, but basically the same old Ethernet that we know and love. We're building a multi-line communications controller and a MagTape controller, which we expect will be the largest controller. 11 types of boards, plus 3 controllers to support early software development, a controller for a display that's somewhat simpler than the final display controller, a controller for a Model 31 disk, and a controller for the honest-to-goodness Ethernet. Okay, that's a total of 14 board types. Shoot.
Full-page display controller, that's 2-board controller, that is 2 different types of controllers, right?
The full-page, yes, there are in fact 2 instances of the full-page display controller. I'm sorry. By the way, please interrupt with questions if you have them. This is what it looks like. Okay. Schematically, let's see if we can't do a little better on the focus. Maybe I better just leave well enough alone. Yeah. The thing that is being built in EOD is the thing called the ESS, the electronic subsystem. And this thing is a box. Looks remarkably like an Alto. It's 19 by 22 by 29. It has a 16-slot backplane in it for these 11 by 14 cards. Power supply. It has a floppy disk, unlike the Alto, because of the requirement for compatibility with both with previous Xerox products, that is the 850 line, and the competitive IBM word processing products and those made by others. We really need a floppy disk. So the consist of, and a power supply is in the central console that supplies the cards and the electromechanical stuff that's in the console itself. Total of 16 slots, of which the CPU occupies 4. The I/O controllers, there can be from 1 to 8, and memory there can be from 1 to 8. And if you use 96K boards, that means you can have 3/4 of a megaword in this box. The remote interfaces are shown on the right. The full-page display controller, which is basically a terminal. It's a terminal, and there is a terminal interface protocol, which is similar to the protocol which is now being adopted for ROS printers, which will allow, we hope, essentially any kind of terminal that obeys the protocol to be plugged in. We can build converters for plugging in Alto terminal, present Alto displays, or we can operate high-resolution displays, and in fact, even color displays. And the protocol and electrical characteristics are such that that thing can be 100 feet away. So it's a little more flexible than an Alto display. The Xerox wire interface looks like the Ethernet. That is, there is a wire that springs out of the back of the machine and runs into the ceiling, where there's a little box which taps onto the coax, which runs throughout the building and actually does the signaling. There can be a local printer, and then there is a remote peripheral interface, which can be quite long, several hundred feet, on which one can string mag card units and floppy disks and little terminals and whatever you might want, with a simple I/O protocol similar to an 8080 bus. Okay, the machine is being built from Schottky bipolar T²L. The basic technology is a bit faster than the Alto, but not as fast as the Dorado. We're making use of 16K RAMs for the main storage, 4K RAMs for the processor control store, multi-layer print wiring boards, 11 by 14. We have some pictures of those a little later, and high-efficiency power supplies. Most of this componentry is reasonably new. We'll have to do that because if we don't, it will be obsolete by the time the machine is sold. So we have had some troubles with just acquiring these components, and in fact, some of the people here have found their stores of 16K RAMs depleted at night by the Janus program, for which I thank you. So the external characteristics that are visible to the programmer are these, in short. The machine is designed to execute the MESA instruction set. That is an augmentation or upgrade or whatever of the MESA that runs now on the Alto. And the main storage rate, or the MESA instruction rate, is about a MIP for the short instructions, for the loads and the adds and things like that. Slows down quite a bit for the longer instructions, the procedure calls and so on, which are basically memory limited. The main storage bandwidth is 200 megabits per second, which is 10 times the bandwidth available from an Alto. And very often we get asked the question, why don't we buy a processor? Why do we want to build our own? And this is one of the reasons. If you look at the characteristics of things you can buy from typical mini-computer vendors, which is sort of the cost class of this machine, you will find that the ratio of the instruction execution rate to the memory bandwidth, the maximum bandwidth that you can draw out of the memory for an I/O device, might be on the order of 10 megabits per second of memory bandwidth to 1 megabit per second, to 1 million instructions per second, or a ratio of about 10 to 1, where this machine is on the order of 200 to 1. And that disparity is one of the principal characteristics of this system as opposed to a typical mini-computer. And that's needed because in a large number of applications, particularly things involving raster scan displays and raster printers, where you really would like to supply the raw bandwidth requirements of the device directly from the main memory of the CPU in order to save cost, you need this kind of bandwidth. An Alto display draws a continuous about 20 megabits per second from the Alto. An 850 display draws about 50 megabits per second. A 10-inch per second ROS, depending on its resolution, can be as high as 80 megabits per second, or maybe even higher. I'm not sure of that number. But these numbers are all up in the 50 to 100 megabit per second range. So this is a comfortable but not enormous margin for applications of that class. The processor is microprogrammed. It's multitasked, similar to the Alto. That is, at the microprogramming level, the hardware is switched on a very rapid basis, typically every microsecond or so, among up to 16 tasks which compete for the use of the processor hardware. And one of these tasks is used for the emulation of the MESA instruction set. The other 15 are used for I/O controllers. And what that does is, as in the Alto, allow the controller hardware to be much simpler. The CPU itself is somewhat more expensive by doing it this way, but for larger systems, there's a considerable net saving over building very complicated controllers by doing it this way. The machine provides a virtual memory system at last. 4 megaword now, and we can expand that to 16 megawords. And the real memory can be between 64K and 768K. And again, when 64K MOS chips become available, we believe that can be, we've planned and put the necessary stuff into the machine so that can be expanded to 1 million words. And then there are a lot of small internal I/O devices that are really part of the processor. An RS-232 communications interface, the interface that I mentioned earlier for the remote peripherals, and a lot of interval timing facilities for timekeeping, a time of day clock, those kinds of things.
Chuck, will you be saying anything later on about the degree to which the E0 processor is specialized to execute the MESA instruction set?
Yes, I will. I'll be saying a little bit about that.
How much hardware for virtual memory support?
I will talk about that a little bit later. Not a whole lot is the answer. Let me skip rapidly through these. The controllers are a thing called the UTVFC, which if pronounced that way makes a lot of sense, but if pronounced user terminal variable format controller makes much less sense. The idea behind this gadget is that it can run from 1 to 4 display and keyboard units. If you remember, the idea here is that the keyboard and display are an integral unit and communicate over a common set of wires with common protocol. This, of course, can't be 4 50 megabit displays because that runs you out of memory bandwidth, but you can run 2 50 megabit displays and 2 televisions, for instance, or 4 sort of standard television sets, or yeah. Basically, the idea is 2 high-speed displays, 850 displays, 4 alto class displays, or 2 alto class displays, or 4 standard 525 line television sets. And it turns out those combinations all absorb about the same bandwidth, that is about 100 megabits per second. And the idea behind this controller is it is the low-cost end of the thing for clustered applications, because all of the buffering for the bitmap, that is for the raster that you see, is in the main memory. And then the common terminal interface is used. All of the sort of standard things for scanning the keyboard, maintaining the cursor on the screen, and in fact the overall control of the thing is in the CPU microcode. There's a second type of controller which we are building for the pathological cases in which a given customer wants to hang 23 large display units on the machine and is willing to do that at the expense of doing no computation. Okay. The buffered user terminal full page controller runs exactly 1 full page display and nothing else, 50 megabit version. It has 1 million bits of memory on the card, which is the raster. So it draws no refresh bandwidth from the main memory. And the single ESS can operate up to, well, your choice. I mean, since it takes no bandwidth when it's running, 10, I guess, the number 10 is limited by the number of available slots in the backplane, not by the bandwidth. And again, it uses the common terminal interface, so you can, when you get wise, you can replace it with something else. Okay, disk controllers, there are 2 flavors. The first one is an exact emulation of the Alto disk, so that software development can proceed with vigor. It operates from 1 to 4 Diablo Model 31 drives. It's an exact emulation of the Alto. Okay, you can put an Alto disk into a D0, boot it, and it will run. And the only difference is that at some place on the disk there must be the D0 microcode. And the programs that you run cannot make use of any of the Alto microprogramming features. But that includes essentially all of the standard Alto software now. It does not use that, or at least can be convinced not to. The second unit is the rigid disk controller, which will actually be brought out as a product. This unit will operate Shugart 4000 series drives. These are some very nice new drives which are very similar to the IBM System 32 disks that Shugart has just announced. The disk is a sufficiently demanding application that there's actually a little sequencer for that disk, which is essentially a little microprocessor itself right on the controller. And right now it appears that error correction is not necessary for that disk. Its reliability and error rates are quite good. But we're arranging things so that we can do that if we need to. And that is the end of those. Okay, for Mesa, we've put a small amount of hardware into the machine, which goes a long way towards making increasing the Mesa execution rate. And basically, there are 4 things. There's a little bit of hardware which buffers 8 instruction bytes. The Mesa instruction set is a byte organized, is basically a string of bytes. And what the hardware does is it fetches 8 of those bytes, 4 words from the main memory, and buffers them, and is willing to peel them out to the emulator microcode on demand. So effectively, the emulator does not have to worry about fetching instructions. That's done by essentially a little process off on the side, and that process is only invoked when the emulator runs out of, or when the buffer runs out of data. So it's not a cache, and in fact, if you sit in a tight loop, it will still fetch 8 bytes every time you do a jump, but it will help a fair amount, we believe. manifested in hardware. That is, there is a pointer which can access the central registers of the machine, and the operations are made available for that pointer, which mirrors the kind of operations that the MESA instruction set wants. The MESA instruction set believes that the main memory is more highly structured than a typical mini computer. In particular, there are a number of pointers which tell you about the local context. The reason for providing those is so that most instructions can be represented as 16-bit quantities, even though they're really 24-bit pointers. So there is, for instance, the base of the current code segment exists in a register. That's a 24-bit quantity that points to the code, and then the program counter is a 16-bit offset from that. And actually, it's a 16-bit byte offset, so code segments can be only 32K long. There's a pointer to the local frame of the currently executing procedure. The local frames are allocated when the procedure is called and released when it returns control to its caller. There is a pointer to the global frames, which are the static data of the computation, and there is a pointer to a thing called the main data space, which is a region in which most of these other structures are actually allocated, which is provided primarily for again for allowing 16-bit pointers. Those base registers are provided. Those and several others actually are provided in the hardware, and the memory access operations are optimized to make use of them. There's a fair amount of hardware for providing the field access constructs of the MESA instruction set, for inserting and extracting subfields of a 16-bit word from arbitrary words. Let's see if I don't have a picture. Okay, I have a picture of the memory system. Not a picture, but the characteristics. Okay. The memory is a 22-bit space, and all pointers are really 24 bits, but it is disallowed and in fact trapped to supply an address to the memory system which has those bits anything other than 0. Well, you can see this slide was not quite for this audience. The memory is paged into 256-word pages, and the map is implemented as a table lookup. For a virtual memory this large, that's somewhat unusual and made possible essentially only by 16K RAM technology. On every memory reference, the sequence of events is the processor launches one of these 16-bit quantities. It is added to the appropriate base register. It does one fetch into the map memory, and that produces the top 12 bits of the real address, and then that 20-bit address is used to access the main memory. A long sequence indeed. And in fact, the access time of the memory system is about 3/4 of a microsecond to allow all of that to go forth. The bandwidth of the memory, on the other hand, is very high. You can issue a new request every 210 nanoseconds, and each one of those requests can transfer up to 4 words of data, and that's about 160 megabits per second, if I did my sums right. And there are some other modes explicitly for I/O devices which allow 16-word transfers to take place, which increase the bandwidth up to the 200 megabit per second number. It's actually a little more than that, providing everything works at the rate that we calculated it at. So, yeah. Here is the structure of the CPU. Okay, this is a fairly simplified picture, and it's drawn out of scale. That is, it emphasizes the internal structure of the processor rather than the overall structure of the system. Basically, the stuff above here is all on the 4 CPU cards that I mentioned, of about 150 ICs each. There's a 4,000 word by 36-bit control store. Microinstructions are 36 bits wide. There are 2 flavors of microinstruction. The first is the sort of normal instruction which just manipulates the data in the registers that you see here on the slide. And an entirely separate instruction form is provided for memory references. This is different from the Alto and, in fact, different from the Dorado and from Max. The idea behind doing that is that you want to be able to specify at the time a memory reference is issued all of the information required to complete it. In particular, you want to specify the address, you want to specify the source or destination for the data, you want to specify what base register should be used to do it, to supply the base pointer. And you want to hand that, from the standpoint of the microprogrammer, what you do is hand that to the hardware, and the hardware, in accepting it, makes a promise to deliver or take the data that you instructed it to. You do not have to, in typical microprograms, wait then for the memory to do its thing. It will do its thing, and it will deliver the data to when you do a processor fetch. You specify which R register, which of these 256 R registers you want the data to appear in, and sometime later it will appear. If you try to access the data from R before it arrives, then you will be stopped. Your program will be stopped, and even at the micro level, that's of no concern to the programmer. So specifying all of that takes a fair number of bits, and so for that reason there are 2 different formats of instructions. The data manipulation instructions that are provided are very similar to sort of any garden variety microprogram machine. It looks a little like a Dorado and an Alto smashed together. And the principal data paths, as I say, are shown here. The principal bus in the machine is the R bus because it provides the data highway from the R registers to the ALU. There is a T register, which is in fact task specific. So again, at the micro level, you need not worry about saving the state of a computation when tasks are switched, because the only state that you really have is the T register, and that is saved automatically for you. Or it's actually not saved. There are multiple copies, 1 per task. There is a full barrel shifter in this machine, and in fact there is, as I mentioned earlier, a fair amount of hardware to do field insertion and extraction even at the microcode level. There's a field of the microinstruction which can be used as a descriptor to insert or extract a field. So we believe that many of the operations which are very, very painful on the Alto will be quite pleasant to program on the D0. The mapping hardware is fairly intimate with the rest of the machine. Basically the idea is that during a memory reference, the ALU, there's only one of them, is the thing that does the base register addition required to add the 16-bit displacement provided by the microprogram to some base register. All the registers are really contained in here, okay, and there are enough of them that that's feasible. The stack pointer points into a region of that. The base registers, when you talk about the memory base registers, you're really talking about a pair of R registers. All of these data paths are 16 bits wide. This is a 16-bit machine. And the fundamental flow of data is, in a single instruction, you read something out of an R register and may shift or mask it and run it and some value previously loaded into the T register through the ALU and back into the H3P register, from whence it is rewritten either into the R memory via this path or into the T register. Instructions are overlapped so that it's possible, even though an instruction takes actually a total of 280 nanoseconds to execute, a new instruction can be issued every 140 nanoseconds. And instructions are actually executed in 4 70 nanosecond phases. The first phase reads the R and T registers. the second and third phase does the ALU operation, and the fourth phase does the rewrite, and they're all nested together such that those things are pipelined right along. There are a few internal registers, not very many, things which have specific function for the MESA emulator, like the stack pointer. There are some registers which provide specialized control for the bit-blit operation. Bit-blit on the D0 will go approximately as fast as memory transfers go on the Alto. So many of the display-oriented applications which have been brought up on the Alto will perform spectacularly on the D0, at least relative to the Alto. It actually stands for H3 processor. The levels of the pipe levels of the machine are the 1, 2, and 3 levels. Actually, there is no 2 level anymore. There's only 1 and 3. The way these things are drawn, there's an intimation of a register there, and there actually is. This register is called H1, and that one's called H2, replacing the 2 level. They actually are all clocked at the same time. So H1 and H2 are loaded at the end of the first phase of the instruction, and H3 is loaded at the end of the third phase. So that's how it gets its name. P for processor. There are, down in the crossbar switch, there are some other registers which are called H3M and H3I for memory and I/O. So the processor is quite tidy and small, and most of the work is actually done down in the memory. And in fact, most of the hardware in the machine is actually related to the memory too. The balance of the logic is one board has to do with the control, just the microstore delivering up microinstructions. There's one board that has to do with the ALU, the central data paths. There is one board which controls the memory and has the data paths for the memory on it. And there's one board whose sole function is to supply the mask and cycle count for the barrel shifter. It also has the interval timer on it. It turns out that's an enormously, not complicated, but just massive function. So logically, it's a little lump right here, but it in fact takes almost an entire board. The memory system is a little bit odd. It is single-ported, although there are 2 buses. There's an inbound data bus to the modules and an outbound data bus from the modules. The modules are quite simple. They really contain only a single register for input data and the storage chips themselves. All of the action goes on the control board, including the error correction and all the switching required. And essentially what's going on there is a 3x3 crossbar switch, where the 3 ports are the processor via this bidirectional R bus, the storage modules, and the I/O controllers. And in fact, there are 2 address buses, one for the addresses of I/O devices, which are 8-bit quantities, and the other for the storage, and those are 20-bit quantities. But basically, it looks like that. I've looked for a long time for a sort of a pleasingly symmetrical way to draw this picture, and I like this one because you can see what's going on quite clearly. The memory is actually pipelined, and there can in fact be 2 references in progress at any given time. And the controller keeps everything sorted out so that you start a reference, and there can be data coming from an I/O device and going to a storage module at the same time. For instance, that data is coming from a storage module and going through the processor. And the routing is all done by the memory control card. And there is not a whole lot of interference, it turns out. Everything fits together very nicely. All of the buses to the storage modules are in fact 16 bits wide, as well as the internal buses of the processor. That's mainly for cost reasons. Drivers and receivers are the expensive thing, and making a thing faster is not very expensive, so it's better to have a faster bus that's narrow than a wide bus which is slow. And in fact, even though the data is transferred in 16-bit chunks, logically the main memory looks like it has 64-bit words, and the reason that we chose to do that was so that the error correction, which which goes logarithmically as the width of the word, will be minimized. For typical mini-computer error correction schemes that use 6 Hamming code bits to correct over a 16-bit word, you're buying a lot of memory. Here we use 8 bits to correct over 64-bit words, and that turns out to be 12% overhead rather than about 40. So that is an enormous win, because in a machine like this, particularly machines for the really high bandwidth application, there will also be a lot of memory in addition to having it just be fast. So the primary component of the system cost is actually the memory. And that trend is getting more and more to be the case. I mean, as better component technology depresses the cost of a processor, the cost of the memory stays the same, or decreases at the same rate, but the dramatic advances come in the central components, and those things shrink away to nothing, and the natural avariciousness of users and programmers wants more and more memory. So the balance shifts, and anything you can do to cut down on the amount of memory used is money well spent. That does have one interesting implication for the processor. Because the processor deals with 16-bit quantities and the memory needs to error correct over 64-bit quantities, all references that are to less than a quad word, and the processor can in fact do quad word references and cause 4 R registers to be transferred. References that are less than that are in fact done as read, modify, write references, and that means that they take twice as long. So the interesting property is that the more data that you pass back and forth between the memory, providing you do it in the right way, the faster the machine will be. So if there's even some reasonable hope that when you write a microprogram, your program can make use of 4 words rather than 1, you ought to take them, because it will in fact take just as long to get or put 4 words as it does to get or put 1 to the memory. Another sort of major glaring difference between this machine and the Alto is that where the Alto has a very tight and intense interaction between the CPU and the I/O controllers, there's more of an arm's length relationship here. There is an honest-to-goodness I/O bus. There is an honest-to-goodness I/O protocol that I/O devices must obey. The result of that is that they cost a little more, but they can actually be designed by more than 3 people sitting around a table. And may be maintained in the field. We will see about that.
Pull that off. You said that if the processor makes a memory request and then goes and says read something into R register 5 and then goes to try and get it, it'll hold out. What's the mechanism that's used to make that work?
The mechanism that's used to make that work is that every time the processor generates an R address, the memory pipeline controller has the source or destination address of the data in it, and it's carrying it along with the steps of the memory. There are 2 comparators which look into the pipe and say, is this address equal to that one? If so, stop the machine. Fair amount of logic to do that. We hope it will pay off.
Sugar disk, this disk is what we use for fast storage.
Yes.
Which one on the storage? Sugar 4000.
The Sugar
4000 you know, this disk.
Yes.
Where are you going to use?
Where?
Can you point out, can you point out where?
Oh, where is it in here? It hangs off one of the I/O controllers. That is, there is a.
Not the storage mode.
Oh no, these are MOS, random access. This is the main storage of the machine. The ShoeGuard is a swapping store. Let's see. That is basically all. Oh well, why not? This is a typical Mesa instruction and how it gets executed, and real microcode. I think, Don, is that real microcode? Close. This is how the load local byte instruction works, just to give you some flavor of the way the machine is coded. And the basic idea in LLB is that, okay, the thing there is the memory, okay? And the L register points to the base of the current local frame, which is some size, and within that it may be smaller or larger than a 256-word page. It does not have to lie on page boundaries or anything. Given a quantity B, which is an 8-bit quantity and therefore can address up to 256 locations relative to the L register. What load local byte says is pick up that 16-bit word from the memory location, which is B locations beyond the L register. And that's done in 4 steps, 4 logical steps. First, you must add B to the contents of the base register, which holds L. That B is an 8-bit quantity. The base register is a 24-bit quantity, which changes whenever the L register changes. And that produces the 24-bit virtual address. Then you must take the top 14 bits of that, which are the virtual page number, use them to access the map. And that will give you back a 12-bit page number, real page number now. Concatenate that with the original 8-bit word number and to form the 20-bit real address. Yes, 20, good. Access main memory, take the resulting data, and stick it onto the stack. The microcode for that is the following. Okay, yes, I will indeed. And this is all there is. 3 microinstructions, 450 nanoseconds if everything's running right, although it usually doesn't.
Is the stack a real 20-bit pointer, or does it go through the same process?
The Mesa instruction set, the stack that the Mesa instruction set knows about is only 8 instructions deep, or 8 locations deep. It's a very small stack, just for evaluating arithmetic expressions mainly and passing arguments to procedures. These 3 microinstructions, you get there by magic, and I will describe getting there as exiting from this one. And basically what you do is you ask with this next data command for the next byte from the instruction stream. That's the little byte buffer that I talked about earlier. You put that into the T register. You do an instruction whose sole purpose in life is to notify the hardware that you're doing a new instruction so that it can save all the necessary information that it has to save about the current state of the computation so that if you get a trap, you can restart. And that's the second instruction. It's basically just a waste from the standpoint of actually getting any useful work done. And the third instruction is a memory class instruction, which in one instruction specifies to do a fetch of one word to the processor using the L base register as a base, and implicitly also using the T register as an offset, to use the stack pointer as the destination for the data and to do the reference. And that's all there is to it. Actually, there's a small error here. In addition to that, the microinstruction should also contain a return operation, which, because of the next inst part of the next new inst operation, has caused the program, essentially the program counter, to be loaded again from the instruction, from the next byte in the instruction stream, and then that 8-bit quantity is used to dispatch off to the next instruction. So normally instructions are like this, which do very little computation, will be quite fast. For a large number of common cases, things like expressions of the form, things like I gets I plus 1 in Mesa, if you look at the sequence in which instructions overlap, you'll find that the machine can, in fact, almost achieve this kind of rate, which is almost 2 million, a little more than 2 million instructions a second. Of course, the problem with instruction statistics is that the slow instructions really drag the rate down, and the Mesa procedure call instruction in particular is very complex, and in fact one might almost say bizarre. I think this week it does 13 memory references in the course of its execution, and since those cannot be done faster than about a half a microsecond each, it's like a 6 microsecond instruction, where these are half microsecond kinds of instructions, and that will take the average way down. So, but the speedy ones are speedy.
Without the addition of P2L, I mean, that's not in the code.
That's done automatically at the time by the memory reference instruction. It's implicit in the pfetch. Okay, so that's most of the things that we're doing, and I'm mostly on time. Let me show some slides, which are sort of the world across the street. What you see on the right is the D0 sitting on a table. We're doing, as with several of the other machines that have and are being built around here, using an Alto very heavily in the checkout. We're using the Midas debugging program, which was originally developed here for Macs and now is being used on the Dorado. We're using all the design automation stuff that was developed here to build the thing. This is a good view of the card tester and the back of Brian Rosen's head. By looking at pictures like this, you never ever find out what the engineer looks like. You only get to see the back of his head. And this is in fact one of the boards. We have built for the machine a card tester which can exercise the functions of the card at low speed under control of the Alto, and in fact have written a fair number of test programs which are written in a variant of BCPL to run the thing, and that has worked out to be a highly satisfactory procedure for bringing the system up. Basically, it has been the case that when we finally plug the system together into the backplane, it usually works within a day. I mean, we make a major revision to something and test the thing out on the card tester. When the card works in the tester, it will then work in the system within a day. That is a card. It's a little hard to see this. These cards are about 11 by 14, and they are built with the Stitchwell technology that was originally gotten for the Dorado, and now is being used several places throughout Xerox. Basically, the way the machine works is the little yellow things are actually wires, which are welded to the little gold-colored posts, and we have a machine over there which drills the wire out of a welding head and moves the board underneath the head to run the wires around, and when it gets to the point that it wants, the operator makes a weld. This turns out to be an absolutely first-rate technology, and the reason for that is that the board is not very tall. If you remember wire wrap boards, they are on the order of an inch thick, and so the systems that you build with them are A, cumbersome, and B, not like they will be when you finally use printed circuit boards. Here we have a reasonably exact emulation of a printed circuit board, but in fact it's possible to build one of these boards in the order of a day from the time you have the information required to build it. And the welding machine is in fact coupled up to the design automation system, so that from the time the engineer draws the logic diagram on his Alto, there is no further human intervention essentially until the welder is actually run, again under control of an Alto. That's just worked out very well. Another picture of the machine backwards. This is the front view of one of these boards. The thing has 167 integrated circuits. The little gold posts on the other side. On this side are integrated circuit sockets, and the little black bugs are the integrated circuits. Many of these devices are the newer sort of 20-pin devices, which are quite a bit more dense than the original sort of T2L that the Mac system and the Alto was built from. The boards aren't a whole lot larger, but they're much more dense as a result of using better componentry.
They get hotter?
They get a bit hotter. Here is the back plane with one board mounted on an extender card, another board in. You can see the cooling. The three circular lumps pointing up from the cards are the fans. The entire machine draws about 300 watts from that small cage.
That's with the full memory?
That's with the, yeah, it turns out the memory doesn't draw very much power. Yeah, a dead-on view. Close-up of the card tester, not very interesting. Another Another shot of the card tester. This is the back plane. 16 cards. This is really made to give future constructors an idea of how to build it. Those are little test jumpers. Most of the back plane is actually mostly a printed circuit board. Only the area at the right, the first 4 slots, are wired. This is a front view of the machine, although unfortunately it's backwards. This chassis is capable of holding 2 floppy disks and no Shugart disk. We will modify the packaging slightly to allow that to happen. The little gadgets on the left are the off-on switch, a little panel which tells you when you push the red button, which is the boot button, what's wrong if the machine does not boot. Inside mechanical details, floppy disk, more details, more details. It's quite small. The whole thing is only about 23 inches tall. It's a little bit bigger than an Alto. Ah, wonderful. At least one had to be upside down. This is a rear view. Actually, this is a view from the ceiling, I guess. But if you can sort of invert yourself a little bit, you can see the way the cabling is arranged out of a slot in the back. This is the thing all sealed up, but not very well.
The version 2 is going to be PC boards, or this goes to PC boards.
This goes to PC boards very soon. Yeah, actually some PC boards have been made.
And the second level is what? Is made out of what?
This.
You can make level H2. What is it called? The second version that's in the pipeline.
Oh, the second version is totally different. It's very much large-scale integration. A lot of the stuff is just an entire board will be replaced by on the order of 5 to 10 ICs, and it's a totally different organization too. Maybe in 6 months I will come back and talk about that.
Xerox specially made chips.
Xerox custom-made chips. Yeah, this machine is not looking to that at all. That is, there's no attempt to have compatibility to anything other than basically the Mesa instruction set level between those 2 machines. So that is the D0 that is being built now, and I'm 1 minute early. May I take 60 seconds of questions? That is an interesting question which is being looked at now, and you know how it's being looked at as well as I do. It's a complex question. I mean, because it's a product program and all of that. We'll know pretty soon when you can have one.
About how many of this design of the machine will be built, or do you know that yet? That is, as opposed to the LSI design, or as opposed to the PC design?
Estimated, of this very design, probably fewer than 100.
And the PC version of this design?
Large numbers of tens. That is, for this guy, about 20 will probably be built. For the PC version, large numbers of tens, and then for the final version, small numbers of thousands.
Was the final version
No,
of the LSI?
final version of the MSI. Several thousands is a small program by Xerox standards. And for the follow-on machine, who knows? It depends on how well people like the kind of things that have been done on this hill for the last 7 years.
Estimated parts cost for the end of this year?
This machine, without any peripherals, can be built for a cost, and I don't know about now, but estimated in early 1980 of about $3,700.
But 1980 is a long way away with respect to that availability.
The principal swing is the cost of memory. It's fruitless to ask what memory costs now. I mean, it's going down like this, so you miss a little bit this way and you're off by 20%. So I just don't know. Thank you.